synchronization performance using circular statistics. So first step is to convert every step in a trial onto a circle in terms of its relative phase from the beat. So the hypothetical beat location is always at 0. So circular statistics helps us account for instances where we want to account for using negative and positive values. So when each step is early relative to the beat, it produces a negative asynchrony, and when it's late relative to the beat, it's a positive asynchrony. When you try to analyze these negative and positive values together, you come into trouble when you analyze them using normal statistics, because what that will do is average these negative and positive values, which could create an artificial zero, or essentially it doesn't capture the whole picture. So that's why we always need to use circular statistics for tapping data. So a first way, an easy way to think about this is to draw them using circular histograms, so rows plots. In this case, here you can see that if you think about this in terms of a frequency density, this shows that the mean asynchrony, so what you're plotting here is the mean asynchrony relative to the beat. The mean asynchrony is pretty close to 0 where the big beat is, even though there are some trials where it's off. So some trials where it's off by 90 degrees, so it's late, or it's pretty early. On average, they are at on the beat. So to do that, first you need to normalize each asynchrony. So an asynchrony is simply the step or the tap time minus the beat time. So if the step time comes before the beat, then the value is negative, and if it comes after the beat, then the value is positive. So you first do that. First, to convert for stats, you'd have to normalize that by the mean, or by the nearest interstep or intertap. Let's just use steps for now. Let's ignore the possibility of using taps, because we're talking about steps in this instance, just for simplicity's sake. But you can use this equally with, this is most commonly used with tapping data. Okay, so I would have given you a different program that would have done this all for you using a LabVIEW executable. And that would have produced files that look like this. So it will give you files, it will give you repeatedly the subject number, the step number, the beat time, the step time, the sync error, so the difference between the two, the asynchrony. So I'm just going to call that asynchrony just for consistency. And then just the unsigned sync error, or asynchrony, and that converted into degrees. So that the formula in the executable would have converted that into degrees for you, so you don't have to do that. In these values, there are some instances where it's not a number. The reason why that's not a number is because the nearest interstep interval would have been greater than 1.5 seconds. So that means that the subject has stepped off the mat, and therefore we don't want to normalize that relative to that very large value, so we do not analyze that particular value. So you can see here that that's one subject in one trial, so this is just the trial number, and that's the next trial, so that's the same subject F91 in the next trial. So I would have also produced that program that you ran would have also produced a sheet that looks somewhat like this. So instead of representing everything in row by row, we here represent things column by column. So that's subject number 91, step 1, step 2, step 3, step 4. Subject 91 again, but this time trial 2, step 1, step 2, step 3, step 4. And this is for a pre-specified experimental conditions, songs 85, so 85% of the subject's preferred walking tempo. So the first step you have to do is remove these not a number values. What those not a number values are basically when the subject walked off the mat and we cannot normalize properly. So therefore we do not analyze those bits of data. So what I'm going to do is ask you to hit Control A to select all the data and then remove those not a numbers. Remove those not a numbers. So hit Control F and then remove all the not a numbers. So find the not a numbers and replace it with nothing, just a blank space. So just don't even hit a space, it'll be just nothing. Replace all, and then what you then can do is transpose those values. So what you're going to do is hit Control C and then you go to the next sheet, new sheet. I'm not going to do that, sorry, I'll just do that again. Control A, Control C, new sheet, Control right mouse button, paste, and then transpose. So we're gonna ask you to transpose all those values. Okay, now that's all done, then you can then go ahead to remove all those blank cells, so because they're a little bit confusing to have those blank cells. So hit go to blanks and then it will select those blanks. Then you press delete on your keyboard. Doesn't do anything. So sorry. Right mouse button, delete, and then hit shift cells up. So then those cells have shifted up. So those trials are now accounted for properly. And then what you can now do is copy those values into a pre-made sheet that I have made for you, where you have all the raw data in this first sheet. So first go ahead and clear that sheet first so that there's nothing there from a previous analysis, and then go Control V into the first cell, so A1 cell. And then what you can see is that in the second sheet here, this check blank sheet, it's just used to check if there are empty cells. So, and here I've also highlighted cells where the values are less than 0. Less than 0 is okay for some programs, but not for all programs. So this is not okay for the program that we're going to use, called Ariana, right here. So we need to convert those values to 360. So we only accept positive values and convert a circle from 0 to 360. A value that is late we denote typically as 0 to 180, and a value that is early we denote as 180 to 360. So all we need to do is convert these negative values to be close to from 180 to 360. So for simplicity, say the value is negative 90, so it's early relative to the beat. When you convert it to 360, all it becomes is 270. So it's basically plus, so that negative value plus 360 is what you need to do for the conversion. So for the conversion, that's in the third sheet here. These are already formulas that have already done the conversion for you. So it basically says if the value is negative, then you do it, you plus 360. Otherwise, you don't do any transformation to it. Okay, so those values are all there. And then what you can do is just copy those values into the program. So I'm going to create a new file. So new angles unidirectional. So axial here seems to suggest that you could do it 0 to 180 and then 0 to negative 180, but it's not really, it doesn't really work for that. So we'd always have to use 0 to 360. And then you want to organize your data in terms of separate columns. So every subject is a separate column instead of group or frequency. And we analyze circular data only. And then columns, I think 100 should be enough in our instance. And then we label them according to the experimental conditions. So this is songs 85. And then you're done. And then what you can do is because you've copied the subject number as well, you can go ahead and paste that into name. That's just a subject number. So you just paste that straight in. So those values are all done already. And then what you can do is start graphing those trials just to have a look at how they look like. So we can have options. Don't print the frequency table because that's not really helpful for us. And then what I tend to find useful is to have the 0, so the beat onset time, at the right side, and the direction being clockwise, I think is useful. So negative values on the right, sorry, on the left. And then that will just plot those pretty quickly. So you can see that here, that's a positive value, that's a negative value, or a value that's greater than 180 degrees. You can see that in this trial, subject number 92 is not really synchronizing. This is a frequency density distribution, so it doesn't actually show that the subject is synchronizing to any particular direction, except maybe a little bit in between the beats, but not really. This value, this arrow here, indicates how long the vector is, so how consistent the subject is. So if it's similar to a probability density function where in your normal curve, the narrower the curve, the less variability there is. So in this case, the longer this is, the less variability there is, and it's very short, so therefore the data is very variable. This black circle here just represents if the value is greater than, if the Rayleigh t-test value is greater than, the Rayleigh test value, sorry, is less or greater than p less than 0.05. So if the value is reliable, then this value would be greater than, this vector would be longer than the radius. So I can show you trials where it is longer. So in some trials, so in this trial it's quite clearly longer, even though the subject was not exactly on the beat. It was always early relative to the beat and still pretty messy, but on average the subject was reasonably clustered in one direction relative to the beat. And here is less variable, more neat data. Okay, so the next thing to do would be to run analyses. So hit an analysis stats, and then what we want is mean angle, variance, standard deviation, length of the vector, and the Rayleigh uniformity test. So I already hinted at this just now. So essentially, if the Rayleigh test is reliable, so it produces values p less than 0.05, that means each asynchrony is not random relative to the beat. So the steps are not random relative to the beat. If, however, it is not reliable, then you can't say, then essentially the steps look random relative to the beat, so they're not actually synchronizing in any way. So what that does is it will give you, if you look here, it will give you the mean vector, so where on average did people synchronize at? Were they early relative to the beat? So in this case, that's early relative to the beat. In this case, it is almost in between 2 beats. And in this case, it is, again, late relative to the beat, and so on. Now, were they random relative to the beat? These guys were, so p-values are clearly less than 0.05. And that's reasonably similarly indicated by those graphs that I showed you just now. So subject number 95 is pretty random relative to the beat, 94 random relative to the beat, and so on. So when we run analyses, what we need to do is we need to export this to a sheet. And we want to run analyses on this circular variance. We want to see if circular variance just tells us how variable were the asynchronies. So the larger the value, the more variable they were. The smaller the value, the less variable they were. And in this case, we're just interested in whether the experimental conditions mattered in how variable they were. Okay, so that's it for now.